Okay, good afternoon and welcome again to the European Non-Associative Algebra seminar. I'm happy to introduce the speaker of today, Pedro Fagundes from the University of Campinas. The title of his talk is The Lubov-Kaplansky Conjecture and Some of Its Variants. Please, Pedro.
Thank you, Salvatore. I also would like to thank the organizers of such nice seminars for the invitation. So I'm going to talk about this conjecture attributed to Lvov and Kaplansky and a few variations of it and how some of these variations can also connect with the conjecture itself. So let's go for it. Okay, I think it's not, okay. So here is more or less the structure of this presentation. We'll go have historical comments about the conjecture and then go for the variations, some variations of it, and then I will focus on the graded setting and graded involution setting for this conjecture. So in this talk, I will be mostly working with associative algebra. So when you see A, think about associative algebra over a field F. At some point, some non-associative algebras will appear as well, but I will make clear when they appear. By f of x, I denote the free associative algebra generated by a set of non-commutant variables x1, x2, and so on. And the elements of this algebra, we'll call it polynomials. And a polynomial that it will be quite important for us is the multilinear ones. So it's just polynomials given in this way, where we have a linear combination of all products of these variables x1, xm, where these variables appear exactly once in every monomial, and these colors are elements from the ground field. So here we are ready to understand the definition of the image of a polynomial on some algebra. It doesn't need to be multilinear, but we'll be focusing multilinear later on, but the definition can be for an arbitrary polynomial. So you take a polynomial and you take an algebra, and then you want to know what is the image of this polynomial on this algebra. So it's just the set of all possible evaluations of this polynomial on this algebra. In other words, you can think the image of this polynomial on the algebra as the image of the function induced or defined by the polynomial f. Okay. So here I have a few examples. For instance, 0 is the image of any polynomial identity for an algebra A. This is the definition of polynomial identity. We can also recover the definition of central polynomials through the definition of image of polynomials. So the field, the ground field, is the image of any multilinear central polynomial for the full matrix algebra, for instance. And we do know that such polynomials, central polynomials, exist for the full matrix algebra. This was given in the early 70s by Razmizlov and Formanek, more or less simultaneously, but with very different techniques. They proved that the full matrix algebra admits central polynomials. We can also realize the space of traceless matrices as the image of some polynomial on the full matrix algebra. In this case, I took the commutator given as xy minus yx. This is a old result given by Schoda in characteristic 0 and generalized by Albert and Mucking-out in arbitrary characteristic, but there are other proofs of this. We will see one of them as well here. And the full matrix algebra, of course, can be realized as the image of any multilinear polynomial such that the sum of the coefficients is different than 0. But we also have another kinds of polynomials, such as this one, the generalized commutator, xyz minus zyx. This was proved by Kuran and Lan. They were actually investigating a more general question. They were investigating the image of this polynomial on not the full matrix algebra over fields, but over more general rings. and they studied this question, but in particular, they obtained this result, that the image of this polynomial on the full matrix algebra is the whole algebra. And here, what I would like to point out is that we can see that 0, the center of the full matrix algebra, the scalar matrices that I denote by F, the traceless matrices, and the full matrix algebras can be realized as images of multilinear polynomials on the full matrix algebra. So a natural question is, okay, is there any other subset of the full matrix algebra that can be realized as the image of some multilinear polynomial, or are just these 4 ones? We have some results so that we can guess that perhaps are just these 4 subspaces that can be realized as images of multilinear polynomials on the full matrix algebra. And here is our first, well, is the result that I'm mentioning, and I just mentioned. We studied instead of the image, we studied the linear span of the image of a multilinear polynomial on some algebra. You can check that this is always a Lie ideal of the algebra. You take associative algebra, take the image of a multilinear polynomial on this algebra, and take the space generated by this subset. You can check that this is a Lie ideal. But actually, we know what are the Lie ideals of the full matrix algebra. They are exactly those 4 subspaces that appeared in the last example. This is a result, a consequence of a more general result given by Einstein in the late 60s. So in particular, if we join these 2 informations here, we obtain this proposition under this mind condition on the order and the characteristic of the field. The linear span of the image of a multilinear polynomial on the full matrix algebra is one of these 4 subspaces. Actually, using graph theory, you can get rid of these 2 conditions here, and you can obtain the same result in case you have 2 by 2 matrices over a field of characteristic equal to 2. But the Hessian result, indeed, we need this condition here. There are more Lie ideals than these 4 ones in case we are not in this situation here. So we rephrase the question, what is the image of a multilinear polynomial on the full matrix algebra? And more than that, we can ask if this image is a vector space or not. This is actually a question posed in that Diniester notebook with a list of open problems in ring theory and model theory. And it's attributed to Lvov and Kaplansky, the second question to Lvov, the first one to Kaplansky, the following conjecture. The image of a multilinear polynomial on the full matrix algebra must always be a vector space. And it is equivalent to say by the previous proposition that this image should be one of these 4 subspaces. So it seems it's simple to understand the conjecture. It seems to be a very easy problem, actually, like exercise of linear algebra, but this is a very challenging problem. We know a positive answer to this conjecture only in small cases. And what do I mean by small cases? We have 2 parameters here. We have the degree of the polynomial and the size of the matrices. Let one of them small, and then we know that the conjecture is true. But if you make this bigger enough, then both of them bigger, then we lose control, and actually the conjecture is mostly open in these cases. But let's see, for instance, polynomials of small degree. If we have polynomial of degree 2, multilinear polynomial of degree 2, then the conjecture is true in these cases. This is easy consequence of the results of Shaw, Albertine looking out about the image of the commutator on the full matrix algebra. We also know for polynomials of degree 3, under some conditions here on the size of the matrices, and the conjecture is still true. There is a recent preprint on arXiv by Daniel Vitas, where he generalized this Decam and Clapp result for multilinear polynomials of degree 3, but he got rid of this condition on the size of the matrices, and also he managed to replace the complex number field here by any algebraically closed field of characteristic 0. So for polynomials of small degree, the conjecture is true. If you go to the other side, if you consider multilinear polynomials of arbitrary degree, but matrices of a small size, like 2 by 2 matrices, then the conjecture is again true. This is a very nice result given by Kanobelov, Malev, and Rowan. They proved that for matrices, 2 by 2 matrices over a quadratically closed field, the conjecture is true. They also managed to get some partial results in the 3 by 3 case. They proved that the image of a multilinear polynomial on 3 by 3 matrices must be one of these 1, 2, 3, 4, 5, 6 subsets. Notice that some of the subsets are not subspaces of the full matrix algebra, but the conjecture is still open for 3 by 3 matrices, because in the result they proved that the image must be one of these options, but they didn't realize these subsets which are not subspaces as the image of some concrete multilinear polynomial. So the image must be one of these, but maybe is not one of them. So it's contained in the set of possibilities of image. So in other words, the conjecture is still open for 3 by 3 matrices and so on. So for this reason, we started to deal with variations of the conjectures. Such problem it's quite challenged. So we started to study images of multilinear polynomials on some other algebras or algebras with additional structure, and then try to understand these variations, expecting, of course, that we could bring some information of these variations to the original conjecture. Okay. So we have some results in this direction. For instance, several authors managed to deal with images of Lie polynomials on subalgebras of the Lie algebra of the full matrix algebra, where the bracket is given by the commutator. And here I mentioned that they worked with small cases, again, small degree of the polynomial or small size of matrices. We also have another nice case, which is the image of a multilinear polynomial on the quaternion algebra, and also on octonions was described. And these two results, they got for polynomials of arbitrary degree, and it's a very complete result. And another type of variation that we can consider is, instead of working with the full matrix algebra, what about working with subalgebras of the full matrix algebra? And this is the case that I'm interested in presenting results and problems here. So the subalgebra that we will consider is the upper triangular matrix algebra that we will denote in this way. And we also denote by J, it's Jacobson radical, which is just the ideal of strictly upper triangular matrices. So upper triangular matrices with 0 in the main diagonal. And then the following question can be posed, and it makes a lot of sense. What is the image of a multilinear polynomial on upper triangular matrices, and also on the Jacobson radical of this upper triangular matrices algebra? So here we have a first result obtained by myself in 2019, where I fully described the image of a multilinear polynomial on powers of the Jacobson radical of UTN. In particular, in the Jacobson radical, if you take k equal 1. And I proved that this image must be trivial or 0 in case you have a 0 polynomial, or you have a polynomial of degree larger than the nilpotency of the Jacobson radical, or must be again another power of the Jacobson radical. Concerning the upper triangular matrix case, I and my master degree supervisor at that time, we got some initial results in this direction. We first studied the linear span of the image of a multilinear polynomial on this upper triangular matrix algebra in trying to get some possible subspaces of the upper triangular matrix algebra that could be the image of these polynomials on this algebra. And then we proved that this linear span must be either the whole algebra or some power of his Jacobson radical. We also managed to deal with small cases, and the situation here is where we have multilinear polynomials of small degree, n equal 2, 3, and 4. Then we proved that the image should be what we were expecting. So must be 0, some power of the Jacobson radical or the whole algebra in all the cases, and some conditions on the ground field. So we started to think, okay, what about the general setting? So what is the image of a multilinear polynomial on the upper triangular matrices, but without these conditions on the degree of the polynomial? And here, a first thing that it's quite important to notice is that the number of commutators appearing in your multilinear polynomial decides the image of this polynomial on the upper triangular matrices, and is somehow one can expect this, because if you multiply m commutators, the image of this m commutators on the upper triangular matrix algebra is the mth power of its Jacobson radical. So the number of commutators appearing change the image. So the question is, how can we compute? How can we identify and compute the number of commutators in a polynomial, in a multilinear polynomial? And actually one can do that via the language of T-ideals. So let me just recall this language and notation that I will use. So a two-sided ideal from the free associative algebra, it's a T-ideal if it is invariant under the homomorphisms of this free associative algebra. So in other words, it's a two-sided ideal where any polynomial inside this ideal, when you replace the variables by other polynomials of the free associative algebra, you obtain always a polynomial inside the ideal. Okay, so this is what we call a T-ideal. We have the idea of the definition of a T-ideal generated by a subset of the free associative algebra, which is the usual one. You just take the intersection of all T-ideals that contain the subset. We will denote the T-ideal generated by a subset in this way. And in case this subset is a unitary set, so we just have one polynomial, instead of using this notation, we use this one. We do not write the brackets besides G here. We just write the polynomial G inside this two wrangle here. Okay.
Polynomials. We're talking about how are polynomials gonna make me and my team better? Just because Mexico is obrigado, vamos por el mundial. We use steroids. Fuck Brazil.
What happens?
Sorry, should I stop? I'm not sure what happened.
Is there any question? Please go ahead, Pedro.
Sorry, okay. Okay, I introduced just the T-ideals of a free associative algebra. So we can check this a descending chain of T-ideals, which is quite easy to check out. So and this chain of T-ideals give us how we will control the number of commutators in a multilinear polynomial, so we can decide what is the image of this multilinear polynomial on the upper triangular matrix algebra. So we define the commutator degree of a multilinear polynomial as a non-negative integer R if this polynomial is a consequence of product of R commutators, but not more than R commutators. So using this definition, Gargatti and Di Mello managed to give a classification to the image of multilinear polynomials on the upper triangular matrix algebra. So they proved that a multilinear polynomial has commutator degree R if and only if its image on the upper triangular matrix algebra is the rth power of its Jacobson radical. So in the same year, Lu and Wang also managed to get rid of this condition of the field being finite, but is not completely. They proved that the field should should have a minimal number of elements, which depends on the order of the matrices. But for finite fields, this is still open. In the graded setting, so let me just recall what basic definitions of the graded setting. So G will denote a group. I will call an algebra G-graded by a group G if I can decompose this algebra as a direct sum of subspaces where I have a notion of degree in some elements of the subspaces, so satisfying this property. The subspaces will call it homogeneous components, and the elements of the homogeneous components will say that has homogeneous degree G. And a subspace of a graded algebra, it's called homogeneous if we can inherit the grading from the algebra to the subspace, so satisfying this decomposition. And the support of a G grading is the elements of the group which indexes non-trivial homogeneous components, okay? So here an example, we can consider a G gradient on the free associative algebra. So we just start with a set of non-commuting variables. We construct the free associative algebra from this set, and we can define a G gradient on this free associative algebra in this way, where we define the homogeneous component of degree G, all the subspace generated by all the words which has homogeneous degree G. So the product of the elements of the group that index the variables in this order is equal to G. And here is the type of the polynomial that we will consider for an analog of the Wolff-Kaplan's conjecture in the graded case. So we have a G-graded polynomial. We will say that it is multilinear if it can be written in this way. So every variable of this polynomial appears exactly once in every monomial of this polynomial. And then we have the definition of the image of a graded polynomial on some graded algebra, which is the usual one, but now we just need to take care about the evaluations that we do. Instead of replacing the variables by any element of the algebra, we must take care about the homogeneous degree of the variable and replacing the variable of homogeneous degree G by elements from the homogeneous component of degree G of the algebra. So as an example, 0 is the image of any G-graded polynomial identity for any G-graded algebra. And if you take a G-graded central polynomial for a G-graded central algebra, the image of this polynomial is the center of this algebra. So in order to discuss an analog of the Wolff-Kaplan's conjecture in the graded setting, we should discuss about gradings on the full matrix algebra and also on the upper triangular matrix algebra. Here, it's quite hard to attack the problem. It's not expected to get a satisfactory answer for the description of images of multilinear graded polynomials on the full matrix algebra with arbitrary grading, or on the upper triangular matrix algebra with arbitrary grading. So we will fix some gradients here, the usual ones and the quite important ones that appears in PI theory, for instance. So here I will introduce the elementary gradients, which appears in the classification of gradients for the full matrix algebra. So you take a group and a sequence of n elements on the group, and then you can construct a gradient on the full matrix algebra in this way. You just put the homogeneous component of degree G as the linear span of the matrix unit is Eij, satisfying this relation. In the same way, you can define elementary gradients for the upper triangular matrix algebra. So the question is, what is the image of a multilinear graded polynomial on these two algebras with some elementary gradient? So is this image a homogeneous vector subspace or not? So that's the question. So in the case of the full matrix algebra, we have some results concerning this, which was given in the last year. But for this case, we will consider the Vaslovsky gradient, which is the gradient induced by the sequence 0 bar, 1 bar, n minus 1 bar, where we use the group Zn for this gradient. So the homogeneous component of degree L bar is just given this way. So you just put zeros, you divide in blocks, put zeros in the main diagonal here, and diagonal matrices in this 1, 2, and 2, 1 blocks of course, of size, depending on the homogeneous component. And then Centroni and Gemello managed to, under some conditions on the size of the matrices and on the ground field, they classified the linear span of the image of a multilinear graded polynomial on this algebra. So it should be 0, the center. Of course, if you since you have identities and central polynomials, graded identities and graded central polynomials for this algebra, so it may appear. Diagonal traceless matrices and some homogeneous component. And they also managed to prove that in case you have small cases, such as polynomials of small degree or matrices of small size, you can get rid of this linear span and you can actually classify what is the image of this multilinear graded polynomial on this algebra. So from 2 by 2 matrices, they managed to prove for arbitrary fields, but in case you have multilinear graded polynomials of degree 2, we need some additional assumptions like quadratically closed field and characteristic greater than P. So the conjecture, since from the last slide, they had some facts to believe that this can hold in general. So if you have a prime number and matrices with size of this prime number over a field, endowed with the Vaslovsky gradient, and we have a multilinear graded polynomial, then the image of this polynomial on this graded algebra should be one of these 4 subspaces. We now turn our attention to the upper triangular matrix case. Here, an analog of the Vaslovsky gradient for this algebra, it is the Zn gradient on this algebra given by this sequence. So we are interested in studying images of multilinear graded polynomials on this graded algebra. But here we are actually going to consider a larger class of gradients, which includes the Vaslovsky gradient for upper triangular matrix algebra, which is a Z-key gradient, where key is a number, integer number less or equal than n, given by this sequence. You just label all the elements from Z-key, from 0 bar up to key minus 1 bar, and repeat the last element in the remaining entries of the sequence. So in case key equal n, we recover the Vaslovsky gradient for this algebra. What about the homogeneous component of this graded algebra? Well, the neutral one is given with copies of the field along the main diagonal and the block of upper triangular matrix of order n minus k plus 1 in the 2 by 2 block over in the bottom. And the non-neutral homogeneous components are given in this way. You just have some in the L plus 1 diagonal here, and you fulfill this k minus L row. And we also define the subspaces of the non-neutral homogeneous component, which are, the subspaces are just given by, you just vanish this diagonal and consider just this row here, but you may also vanish elements from this row from left to the right, okay? And then me and I and my PhD supervisor, Plamen Koshlakov, we, under some mind conditions on the ground field and considering upper triangular matrices with that Z-key gradient that I just introduced before, we managed to prove that the image of a multilinear graded polynomial on this graded algebra must be, or 0, of course, some power of the Jacobson radical of the neutral component. Some of those subspaces B, L bar R, where I vanish the main diagonal and may vanish elements from the row from left to right, or some homogeneous component. As a consequence of this theorem, we get this result which somehow connects this variation of the Lvov-Kaplan's conjecture with the conjecture itself. So denoting Y neutral variables and Z non-neutral ones under some mind conditions on the ground field. We prove that if we have a multilinear polynomial not graded, but every time we replace n-1 variables of this polynomial by neutral variables, but one by a non-neutral variable, we obtain a graded polynomial, which is not a consequence of the commutator of two neutral variables, then we can prove that the image of this polynomial on the full matrix algebra always contains traceless matrices. In particular, we can obtain that the image of this polynomial on the full matrix algebra is exactly SLN, since the inclusion that this image is in SLN is trivial because this is a linear combination of traceless matrices, and the reverse inclusion is we got from the previous theorem. So in particular, we can recover Schroeder's results from this application of these ideas from the graded set into the Lvov-Kaplan's conjecture itself. We also deal with small dimension cases. So when we have upper triangular matrices of 2 by 2 size or 3 by 3 size, we expect to get results that are regardless the gradient. So it does not matter the gradient do you have. We want to obtain results that in the form the image will be a homogeneous vector space regardless the gradient. So to do that, we need to know what is the gradients on upper triangular matrices, and this is well known. This is a result by Valenti and Zaitsev, where they describe it that essentially the gradients on UTN are elementary ones. And also we can work model these graded isomorphisms between the gradients because the image is somehow invariant under this graded homomorphic image. And this holds in general not for associative algebras, but this remark also holds for non-associative algebras. You just need to take care which type of polynomial you consider. If you are in the class of Lie algebras, take Lie polynomials, Jordan algebras, Jordan polynomials, and so on. And to obtain the results in the small dimension cases, I recover these two lemmas that says that if you join in these two lemmas, we have that if the image of a multilinear polynomial on some algebra is inside some two-dimensional space, then it must be a vector space. In case it is inside a one-dimensional space, this is trivial, and we can completely describe the image. But in case it's a two-dimensional vector space, this is not so trivial. This was given in a paper by Malev in 2014. And using these previous lemmas and more technical computations, we are able to give not a description, but we were able to prove that the image of a multilinear graded polynomial on 2 by 2 upper triangular matrix algebra, it's always homogeneous vector space. It does not matter the gradient that you have. You can always prove that it's a homogeneous vector space. And the same result for 3 by 3 upper triangular matrices. In case we have the trivial gradient, we need to take care about this assumption here. We also can consider the Jordan algebra of upper triangular matrices with this product, the circle product, AB plus BA over 2. So this gives us the structure of Jordan algebra in the upper triangular matrix algebra. So it's just this classical construction of giving a Jordan structure to an associative algebra. And then we also managed to describe images of multilinear polynomials on this algebra in case n equal 2. But for this, we need, since we want a result regardless the gradient, we need to know what about the gradients on this algebra. And the gradients were described by Kushlukov and Yazumur in 2017. In this case, the gradients are more complicated than the ordinary case. We do not have only elementary gradients, but we have another type of gradient that they call it of mirror type. So here's the result. If we have a multilinear graded Jordan polynomial, the image of this polynomial on the Jordan algebra of 2 by 2 upper triangular matrices is always homogeneous vector space. It does not matter the gradient that you have. And we also managed to prove this for 3 by 3 Jordan upper triangular matrix algebra with the Z3 natural elementary gradient, which is the gradient given by diagonals. And we proved that the image should be 0 or some homogeneous component. But what is interesting in this result is that most of the techniques that I apply here, I started to work modulo the identities that you have in your algebra. So it's important to know where all identities in your algebra. But in this case, it's still an open problem to describe all graded identities for this algebra with this very simple grading. But still, we were able to classify the image. And here I also would like to discuss the graded involution setting, and this is a very different case. We will see that we obtain very different results, and admittedly unexpected at the first time. Just to recall, an involution on some algebra is an anti-automorphism of order 2. I will assume linear because I'm assuming all involutions of first kind. I'm working with involutions of first kind only. So if you have a graded algebra, an involution on this graded algebra, it's called graded involution if let the homogeneous components invariant. In every algebra with involution, we can always decompose it as a direct sum of symmetric and skew-symmetric elements. And in case you have a graded algebra, you can also check that the symmetric and skew-symmetric parts are homogeneous vector subspaces. And I will denote in this way the free graded associative algebra with involution, which is just the free associative algebra generated by a set of homogeneous symmetric variables and homogeneous skew-symmetric variables. So here we have the space of multilinear polynomials that we could consider, but we will not, because we have a problem here. So this is the space of multilinear polynomials, graded polynomials with involution. However, if we consider this kind of polynomials to expect to deal with an analog of Lvov-Kaplan's conjecture in this graded involution setting, we will have a problem to define not the image of a polynomial, but this image of multilinear polynomials. In general, we define the image of a multilinear polynomial by a function induced by this polynomial, and we have a multilinear function on the algebra. But if you use this space of multilinear polynomials in the graded involution setting, we can have, for instance, this polynomial, which is multilinear. It is in this space, however, does not give us a multilinear function on some graded algebra with involution. So for this reason, we consider this subspace of the space of multilinear graded polynomials with involution, which is just the following. We just fix a priori a list of symmetric and skew-symmetric homogeneous variables, and we consider all permutation, all words in these letters, and we consider the space spanned by these monomials. So this is the space that we will consider of multilinear polynomials. So given a multilinear polynomial, the image of this polynomial on some graded algebra with involution is defined as usual. We replace symmetric homogeneous variables by symmetric elements of the algebra with respect to the same homogeneous degree, and skew-symmetric variables by skew-symmetric elements from the algebra respecting the homogeneous degree. So we can set in the question, what is the image of a graded multilinear polynomial with involution on UTN endowed with some graded involution? So to answer this question, of course, we need to know what about the graded involutions in upper triangular matrices, and this is well known. Under some conditions, there are some hypotheses here that I'm avoiding, but in the trivial case, the involutions are basically reflexive or symplectic, and the non-trivial gradient case, we have certain elementary gradients given by certain sequences, defined by certain sequences of elements from the group, plus reflexive or symplectic involutions. And then we managed to prove that in case we have 2 by 2 matrices endowed with some graded involution G, under some conditions such as the support of the gradient generates G and F is algebraically closed field of characteristic different from 2, which are conditions that come from this second classification here. Then the image of a multilinear polynomial, graded polynomial with involution on this algebra must be always homogeneous vector space. However, this is somehow an optimal result because if you consider the upper triangular matrix algebra with order greater or equal 3, endowed with reflexive involution, we can find multilinear polynomials such that the image of these polynomials on this algebra is not a vector space. What about the non-trivial gradient setting? We can also obtain this analogous result, but in this case, we can prove for 3 by 3 matrices endowed with some graded involution, the image of a graded multilinear polynomial with involution on this algebra will be always homogeneous vector space. But if you go further, matrices of size bigger than 3, so n greater or equal 4, with the canonical Zn gradient and reflexive involution, we can find multilinear polynomials such that the image is not a vector space. So the product of this is that we cannot expect an analog of the Lvov-Kaplan's conjecture in this involution setting or graded involution setting. So it is the limitations of generalizing things. So that's it. That's what I would like to say. Thank you very much.
Thanks, Pedro, for this interesting talk. Are there any questions?
Let me make some comment. First of all, I enjoyed the talk, and I am very happy to attend this lecture.
Thank you.
It made the state of problems in much broader content. Sometimes upper triangle, maybe blocks are 2 by 2. Maybe there are some more complicated grading. So I saw some insight on how to make the state of problem more broad. Again, thank you very much for your talk, and I really enjoyed it.
Thank you, Alexei. Thank you very much for your comment.
Okay. Any other questions? Okay.
I think during my talk, someone asked something I couldn't understand actually.
Yes. Is Giovanni Quirarte there? Maybe not. Any other questions, comments, or remarks? If not, let's thank the speaker again.
Thank you very much.
And we will resume on next Monday at the usual time. Thank you very much. Bye-bye.
Bye-bye.
Thank you. Thank you for the talk.
Thank you.